Hi dear students, our next topic is the curl of electrostatic field. I consider a point charge. There is a point charge Q in the figure that is kept at the origin of the coordinate system. At the origin means at the origin of the coordinate system. Now, if a charge Q is placed at here, then the electric field lines will be emerging away from this charge. These electric field lines will be non-uniform. With a positive charge, the electric field lines will be emerging away like this. Therefore, this electric field, due to the point charge at a distance r, is given by this expression. That is, this charge is kept at the origin of the coordinate system. That is why we have chosen, we have taken it as a r square. Our aim is to calculate the curl of E. The curl of E means what is the answer of curl of E? That is our discussion. We already know that the electric field due to a point charge, that is a curlless, because we cannot see any curl of this electric field. All the electric field lines are straight lines. We cannot see any curl on this field. ഇവിടെ ഒരു ചുഴിയോ ഒരു വളവോ ഒന്നും നമുക്ക് കാണാൻ പറ്റില്ല. Del cross E is equal to 0 ആണെന്ന് നമുക്കറിയാം. But here we are interested to prove this one in another way. Okay, that is our aim is to prove that del cross E is equal to 0 mathematically. Now for this, I calculate the line integral of the field from the point A to B. That is, the point A is here in this figure, and the distance to that point from the charge is this RA. The point B is at a distance RB from the charge Q. Then the line integral of this field from the point A to B, which means if you refer this figure, I consider two point A and point B and calculate the line integral from the point A to B of this electric field. That is nothing but denoted by A to B E dot dl. This we need to calculate. What will be the answer of this one? We know that expression for the electric field, that is, this E can be substituted by this expression. Then what about this dl? dl in spherical polar coordinate system is given by dr r cap plus r d theta theta cap plus r sin theta d theta phi cap. Because why we have taken dl in the spherical polar coordinates? Because the electric field lines emerging away from the charge Q, that will be in spherical direction in all three x, y, z direction, and therefore the length element, if you calculate the line integral for this electric field distribution, then the line integral should be taken as in a spherical polar coordinate system. But here the electric field components have only the r components. If you see in the expression for the electric field, this has only the r component. And if you see the expression for the length element, the components except r cap, that is theta and phi, will not be present while taking the E dot dl. Therefore, the line integral a to b e dot dl can be written as a to b 1 by 4 pi epsilon 0 q by r square r cap dot, instead of dl we can substitute this expression, it is dr r cap. Since the electric field does not contain any theta or phi components, therefore no need to write the theta or phi components of dr also. That is, here this will be 1 by, you can take q by 4 pi epsilon 0 outside, a to b 1 by r square dr. That is, this is equal to q by 4 pi epsilon 0 integration of 1 by r square dr is nothing but minus 1 by r. Now the a and b are the 2 points from the charge. If you refer this figure, then the distance to the point b, that is nothing but this distance given by rb. Distance to the point a, that is given by this one, nothing but ra. Therefore I can write in this expression, instead of a and b, this is a ra and this is rb. Then if I can take the minus outside, then this will be minus q by 4 pi epsilon 0 1 by rb minus 1 by ra. Fine. Then if I multiply with if I take the minus inside, then this line integral a to b e dot dl can be written as 1 q by 4 pi epsilon 0 1 by ra minus 1 by rb, where ra is the distance from the origin to the point a. That is rb is the distance from the origin to the point b. Now if I consider a closed path, that is, if I consider this path is a closed one, this if I take this is as a closed path, then while taking the integral, the point b, but both the point a and b will be at the same position. That is, if I take the closed line integral starting from the point a, then I will go like this and come back this. That is, the point a and b will be at the same place. If a is equal to b, then ra is equal to rb. That is, ra is equal to rb. That is, if I take the closed loop, ra is equal to rb. If the path is closed, then ra is equal to rb. Then the line integral, if you substitute the changes here, the line integral will be a to b e dot dl, that is equal to q by 4 pi epsilon 0 1 by ra minus, instead of this rb we can substitute this ra. Okay, then this term obviously goes to 0. Therefore here I committed a mistake. This should be the closed line integral. It is a closed line integral for the line integral of the electric field over a closed path that is equal to E dot dl is equal to 0. That is, a line integral of the electric field around a closed loop is 0. Fine. Now apply the Stokes theorem, because we were proving that del cross E is equal to 0. Now apply Stokes theorem to the above expression. What is Stokes theorem? It is line integral E dot dl is equal to surface integral del cross E dA. That is, since the left hand side of this expression is 0, sorry, here there should not be any limit, because this is a closed integral, closed line integral. The left hand side of this expression is obviously goes to 0 according to this expression. For this is 0, then from here we can say that del cross E is surface integral del cross E dA also be 0. Or we can say that del cross E is equal to 0. That is, the curl of the electric field vector is a 0. Curl of the electric field vector is 0 means we have already seen that we can express this as a divergence, this as a gradient of a scalar potential. That is, we know curl of a gradient, curl of gradient of a scalar function is 0. That is, curl of gradient of a scalar function means if V is a scalar function, then I can take del V. Curl of gradient of a scalar function is equal to 0, which means here this del V is nothing but this electric field. That is, this vector electric field E can be written as gradient of the scalar potential, but conventionally we put a minus sign here. The reason for why we put negative sign here that I have already explained in the Helmholtz theorem session. Therefore, the electric field can be written as negative gradient of the potential. Okay. However, in the next topic, that is electric potential, we will once again discuss this expression. Okay. Next, our topic is the electric potential. Why we are talking about the electric potential? Because the electric field is a vector quantity. Then to explain all the phenomena arises from the electric charges, explaining all those phenomena using the electric field, that is very difficult, because we have to always obey the laws of vectors while adding, while subtracting, while multiplying, while taking dot product, everything. But if we use the electric potential, that is, the electric potential is denoted by V, that is, the electric potential V is a scalar quantity. Therefore, it will be quite easy to calculate all types of phenomena, all types of characteristics arising from the electric charges that can be easily calculated by using the electric potential. Since the electric potential is a scalar quantity, we can simply treat these electric potential as numerical values, like while subtracting, while adding, or while multiplying, then no need to worry about the vector loss. That is why we are introducing the electric potential here. You have already learned the meaning of the electric potential and its definition in the +2 classes. However, I would like to recall the definition here. If a charge Q is kept here, of course, there will be electric field lines emerging away from these charges, from this charge. And to find out an electric potential at this particular distance from the charge Q, if the distance is R, I consider that this charge is kept at the origin of the coordinate system. Then the electric potential at this point, that point is denoted by B, and the electric potential at the point B in this electric field can be defined as the work done in moving a unit positive charge from infinity. I am bringing this unit positive charge means I am bringing 1 coulomb charge from the point infinity to the point B against this electric field. That is, here the electric field is offered by the Q charge. If it is a plus Q charge, then if I bring another charge, we denoted by Q0, towards this charge to a particular point B, since both charges are positive, this Q0 charge will experience repulsive force, but against the repulsive force, I am applying an external force and bring this 1 coulomb charge to the point B. Then I need to calculate what is the work done. That work will be equal to the electric potential at this point. That is, the electric potential at a point in an electric field is defined as the work done in bringing a unit positive charge from infinity to that point against the electric force of the field. Okay, once again, the electric potential at a point is defined as the work done in moving a unit positive charge from infinity to that point against the electric force of the field. To derive an expression for the electric potential, once again I draw the same picture. That is, we have a charge Q here. Then I want to define the electric potential at the point B. I had to bring a 1 coulomb charge. Q is equal to plus 1 coulomb charge. This may be known as Q0. I am bringing the charge from the infinity to the point B. While bringing the charge, there will be a repulsive force from this source charge Q, and here Q0 is a test charge. Then the electric field at the point B offered by this source charge Q is given by electric field E is equal to 1 by 4 pi epsilon 0 Q divided by R square R cap. This is the field produced by Q, that is a source charge at a distance R. Then I calculate in the small amount of work done to bring or to move a unit positive charge for a very small displacement dr. Very small displacement dr. This. The work done is given as dW is equal to F dot dr. You know that the expression of the work is nothing but the F dot displacement. Then to calculate the total work done to bring the charge from the infinity to the point B, that can be written as W is equal to, just integrate this one, that is from infinity to the point B, F dot dr. Then what is this F? F is nothing but the electric force. Nothing. This should be Q0, and this electric field is an electric field produced at the point B due to this source charge Q in the figure. This electric field is this electric field. Electric field produced by the charge Q. The Q0 is nothing but 1 coulomb. Therefore, this F can be written as E. Therefore, W can be written as infinity to the point B. E dot, instead of F, I can substitute E dot dr. Here, if you see in the figure, the electric field from the charge will be, since it is a plus Q charge, our source charge, electric field will be along this direction, away from the charge. But the displacement of the test charge, that is be along this direction. There is the electric field is along this direction, and the displacement is along opposite direction. Therefore, angle between E and, that is E dot dr, means this will be E dr cos theta, that is this is equal to E dr cos 180 degree, because here theta is equal to 180 degree. Therefore, cos theta is minus 1, this will be E dr. Therefore, here I can write this W is equal to minus of infinity to the point B E dr. Expression for the electric field already we have 1 by 4 pi epsilon 0 Q divided by R square. Then if you substitute this value here and take the constant outside, this will be Q by 4 pi epsilon 0, the minus sign, integration from infinity to the point B, 1 by R square dr. And this will be equal to minus Q by 4 pi epsilon 0 to minus 1 by R. See, from infinity, the point B, if you refer in this figure, I consider that this point, this is at a distance, point B is at a distance R from the origin or from the source charge. Therefore, I take this as a R. Okay, where R is a distance from the origin to the point B. Or distance from the origin, distance from the charge, because the charge is kept at the source charge is kept at the origin. Therefore, this work done can be written as minus and minus get cancelled. Therefore, this will be 1 by 4 pi epsilon 0 Q divided by R, because Q divided by 4 pi epsilon 0 into 1 by R minus 1 by infinity, this term goes to 0. This work done according to our definition, that is we have written definition, electric potential V is the, at a point is defined as the work done. Therefore, the work is nothing but the potential. Work done in bringing a unit positive charge. Since the work unit positive, since we are bringing the charge Q is of the 1 coulomb, therefore work is nothing but the potential. This is nothing but V, the electric potential due to a point charge Q at a distance R is given by 1 by 4 pi epsilon 0 Q by R. This is expression for the electric potential. Okay. Next we will discuss the electric field as a negative gradient of the potential. That is, we will once again we will prove the electric field as a negative gradient of the potential. Let's consider a charge plus Q. Then at a distance from the charge, that is at the point B, we know that the electric potential V is proportional to Q by R, or V is proportional to 1 by R. At the nearest point B, nearest point, that is at the point B, suppose electric potential is 15 volt. Then if you go away, that is another point, the point A, the electric potential decreases, and I take this potential as a 10 volt. Then if the electric potential at this point is V, this is equal to 10 volt, then the electric potential near the nearest point B from the charge Q is little more, that is V plus dV, where dV is nothing but the 5 volt. Okay, at the nearest point, electric potential will be higher, and at larger distance, the electric potential will be the smaller. Then I am bringing a charge from A to the point B. That charge is nothing but Q0. That is, the displacement is dr. Then by definition, dV is thus. dV means while coming from the point A to the point B, the difference in the potential is nothing but here dV. That is, the dV, there is a potential difference, or the potential at a point is defined as a work done in bringing a unit positive charge from A to B. Okay, this is nothing but dV is equal to work done. dV is equal to F dot dr, because work done is nothing but force in displacement. dW is, dV is equal to dW, work done. The work is replaced by force into displacement. This force is experienced by the Q0 charge in the electric field E, that is occupied by the source charge Q dot dr. Here the Q0, I take this as a plus 1 microcoulomb charge. If you see the figure, the electric field coming from this positive charge will be along this direction, but the displacement, we are bringing the charge towards the left direction. This displacement of the charge is towards the left. Therefore, E and dr makes an angle 180 degree. E dr cos 180, this will be minus E dr. Therefore, here I can write this is a minus Q0 is 1 coulomb, therefore this is a E dr, because theta is equal to 180 degree. E is in this direction and dr is in the opposite direction. There is a left hand side, we have dV, or simply we can write electric field is defined as minus dV by dr. Here we have note down that the E and dr are in opposite direction. This can also be written as, in general, electric field is a negative gradient of the potential. From this, I can write this as a dV is equal to minus E dr or the electric potential between 2 points can be easily find out. Just do the integration. While putting the integration, you have to put a reference point that as the limit, and the point in electric field is E dot dr. Okay. That is, we'll calculate the electric potential in an electric field produced by this point charge q. That is, then this is our point in electric field. We are interested to find out the electric potential at this point. Then for this, we have to bring another charge from infinity. Therefore, the reference point, this is a reference point. Okay. That is the meaning of this expression. The same thing we have discussed just now, that is, if del cross E is equal to 0, curl of the static electric field is 0 because the electric field originating from the static charges are curlless. Curl of a vector field is 0 means we can write the curl of gradient of the scalar function. Therefore, from these two, I can write electric field is the del V, that is negative gradient of the potential. We discussed the electric potential due to a spherical shell. We already discussed the electric potential, and we are calculating the electric potential of various objects. That is, this is a question in the Griffith textbook. That is, find the potential inside and outside a spherical shell of radius r, shown in the figure, which carries a uniform surface charge. Okay, set the reference points at the infinity. Here we have to find out the electric potential due to the spherical shell, outside, inside, and also on the surface. The general expression to find out the electric potential is V minus of, this is a one reference point we have to take. Then the point in electric field, then E dot dr. If I consider Q is the total charge on the spherical shell, and it is given R is the radius of the spherical shell. This spherical shell means, spherical shell എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ നമ്മുടെ ഫുട്ബോളിൻ്റെ ഗേസ് പോലെ. ഫുട്ബോൾ ഉണ്ടല്ലോ, ഫുട്ബോളിൻ്റെ ഉള്ളിൽ എയർ ആണല്ലോ, അതിൻ്റെ സർഫേസിൽ മാത്രമായിരിക്കും അതിൻ്റെ ചാർജ് ഡിസ്ട്രിബ്യൂട്ട് ചെയ്തിരിക്കുന്നത്. അതാണ് ഒരു സ്ഫെറിക്കൽ ഷെല്ല് കൊണ്ട് ഉദ്ദേശിക്കുന്നത്. ഇതിന് വോളിയം ഇല്ല. All the charges are distributed at the surface only. There is no volume for the spherical shell. അതിൻ്റെ റേഡിയസ് ആണ് തന്നിട്ടുള്ള, this radius r. First, we have to calculate the electric potential outside. This first we calculate V outside. V outside means R greater than R regionിലെ ഇലക്ട്രിക് പൊട്ടൻഷ്യൽ ആണ് നമ്മൾ കണ്ടുപിടിക്കേണ്ടത്. ആ പോയിന്റ് എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ചിത്രത്തിൽ കാണിച്ചിരിക്കുന്ന പോലെ, ഈ ചിത്രത്തിലെ ഈ പോയിന്റ് P. അപ്പം എങ്ങനെയാണ് നമ്മൾ എങ്ങനെ വരയ്ക്കും? സ്പെല്ലിൻ്റെ കേസിൽ ഇങ്ങനെയുള്ള സ്ഫെറിക്കൽ ഷെല്ലിൻ്റെ ഈ ഒരു പർട്ടിക്കുലർ പോയിന്റ് ഇവിടെയുള്ള, അതായത് സെൻട്രലിൽ നിന്നും പോയിന്റിലേക്കുള്ള അകലം സ്മോൾ r, അതിൻ്റെ റേഡിയസ് ക്യാപിറ്റൽ R. ഈ പോയിന്റിലുള്ള ഇലക്ട്രിക് പൊട്ടൻഷ്യലാണ് നമ്മൾ കണ്ടുപിടിക്കേണ്ടത്. അപ്പോൾ ഈ എക്സ്പ്രഷനാണ് നമുക്ക് ഉപയോഗിക്കേണ്ടത്. B is equal to minus reference point to the point in the electric field E dot dr. അപ്പോൾ ഇവിടെ reference point here we have to take as the infinity. Okay, Therefore, first I will write the equation. The equation is V out is equal to minus, from where I have to come? I have to come from the infinity. If you see in the figure, I have to come from the infinity to the point where we are interested to find out the, that is, we have to reach at this point. That is, that point is at a distance r from the center. Therefore, the reference starting point, that is, we are coming from infinity to that point, means that point is at a distance r outside the radius. അതായത് നമ്മുടെ റീജിയൻ വരുന്നത് ചിത്രത്തിലെ ഈ ഒരു പോയിന്റിൽ നിന്നും ഈ ഒരു പോയിന്റിലേക്കാണ്. Therefore, ഈ റീജിയൻ നമ്മുടെ പോയിന്റ് പി കിടക്കുന്നത് ഔട്ട്സൈഡ് ദ സ്ഫെറിക്കൽ ഷെല്ലാണ്. അതുകൊണ്ട് ഇവിടെയുള്ള ഇലക്ട്രിക് ഫീൽഡ് എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ it will be the E outside. Therefore, we have to write E out dot dr. What is the electric field outside a uniformly charged spherical shell? Do we already know? We already derived that expression. If total charge contained is Q, then electric field outside is given by 1 by 4 pi epsilon 0 Q divided by R square. This is the electric field. Just to substitute here, this will be infinity to the point R, 1 by 4 pi epsilon 0 Q divided by R square, R dot, what about dr? dr നമുക്ക് എന്ത് വരും? dr is nothing but dr r cap. Therefore, this is dr r cap. Okay, constant പുറത്തേക്ക് എടുത്തു കഴിഞ്ഞാൽ q by 4 pi epsilon 0 minus infinity to the point r, 1 by r square dr. Then integration ചെയ്തു കഴിഞ്ഞാൽ here minus sign is there, minus of q by 4 pi epsilon 0 into integration of minus 1 by r square, means that will be minus 1 by r, infinity to the point r. അപ്പോൾ ഇവിടെ ഈ മൈനസും പോയി പ്ലസ് ആയി. Therefore, this is equal to q by 4 pi epsilon 0 1 by r minus 1 by infinity is nothing but 1 by 4 pi epsilon 0. This 1 by infinity goes to 0. Therefore, this is q by r. Therefore, I can write electric potential outside a uniformly charged spherical shell is equal to 1 by 4 pi epsilon 0 q by r, where q is the total charge contained in the spherical shell. Fine. Now, if I want to express this potential outside in terms of the surface charge density, suppose if sigma is equal to dq by dA is the surface charge density on the spherical shell, then dq is equal to sigma dA, and total charge contained is sigma into integration dA ചെയ്തു കഴിഞ്ഞാൽ 4 pi r square, surface area of the spherical shell, because all the charges are contained on the surface sphere. Spherical shell radius is r, therefore this is 4 pi r square. And instead of this q, I can substitute this sigma 4 pi r square. Therefore, here I can write our V outside. V outside is equal to 1 by 4 pi epsilon 0. Instead of this q, I substitute this one. Is sigma 4 pi r square divided by small r. Here the 4 pi get cancelled. Then finally the electric field outside the spherical shell in terms of the surface charge density is sigma r square divided by epsilon 0 r. Okay. This is the electric potential outside the spherical shell in terms of the charge density sigma. Now we need to calculate the electric potential on the surface. This is the second one. Electric potential at the surface. Surface means R is equal to R. How do we calculate the electric potential at the surface? We have already derived, that is electric potential outside, it is at a distance R. Now the situation is this one. Our spherical shell whose radius is R. Now the point of interest, that is just exactly on the surface. This is R. That is R is equal to R. Then this is a V surface. Then two way we can calculate the potential. First one is simply use this expression and substitute capital R instead of the small r. That is V at the surface can be written as 1 by 4 pi epsilon 0 Q divided by R. This is the electric potential at the surface of the spherical shell if R is the radius and Q is the total charge. Now in terms of the surface charge density, I can use this expression. Here instead of small r, I can substitute capital R, that is V outside can be written as sigma r square divided by epsilon 0 capital R. Here this one and this r cancelled. Therefore, V outside can be written as sigma r divided by epsilon 0. This is another representation of the electric potential. This is not outside, this is at the surface. Sorry, this also should be at the surface. Fine. Now other way, that is we have to calculate the electric potential at the surface. Therefore, the reference point should be from the infinity. We have to come from the infinity. Therefore, the expression is V as the surface minus, we are coming from the infinity to the point R, where R is nothing but R is equal to R. Or simply I can write the point of interest is exactly at the radius. Then from the infinity to this surface, in this region, the electric field is nothing but electric field outside. Therefore, here I have to use E out dot dr. The electric field outside, that already we know 1 by 4 pi epsilon 0 Q divided by R square dr. Then if you do this one, finally you will obtain 4 pi epsilon 0. There is a minus sign here, one more minus sign will come here. This is infinity to the R. This is equal to this minus and minus get cancelled. Then this will be 1 by 4 pi epsilon 0 Q by R, because if you do this integration, this will be R minus 1 by infinity, this time will goes to 0. The V surface will get this form as a final one. This is exactly similar to this expression. Okay. Now let us calculate the electric field inside the spherical shell. Sorry, the electric potential inside the spherical shell. V inside. V inside means the region is R less than R region. For this is our spherical shell whose radius is capital R. We are interested at point P, that is lines here at a distance small r. Therefore, the electric potential V inside can be found out. Then, according to the definition of the electric potential, we have to come from the infinity to the point of interest. We have to reach here. Therefore, this path I will split into two. That is, the first one is while doing the integration, that is, this will be minus. I have to come from the infinity to the to this, that is, come from the infinity to the point that is at R is equal to capital R, is this point. Therefore, minus infinity to R. Then in this region, the electric field is E out. Therefore, E out dot dr. Minus, I have not reached the point of interest here. Still, I have to go this distance. Okay. This region, if I come from the outside, we have already reached here at the point capital R. Next, we have to come from the capital R to this small r. Therefore, the integration is from R to small r. Then, this region is contained inside the shell. Therefore, here the electric field will be E inside. E inside dot dr. In this way, you have to split the integral into two. Okay, that is, in what is this integral? The electric field inside the spherical shell is, I have to come from the infinity to the R dot dr. This path I have splitted. This I have splitted into infinity to the radius plus again minus of R to R. Here you will have corresponding electric field E out. Here this will be E inside, because this region R to R region where the electric field will be E inside the spherical shell. Fine. Just calculate the values here. We know the expression for the electric field outside, because minus infinity to R, we have already done this calculation. However, I will do once again here for your convenience. That is, minus infinity to R, E outside is, I will write E outside, it is 1 by 4 pi epsilon 0 q by R square. Then what about E inside? Inside the spherical shell, anywhere inside, we already derived the expression that there is no charge enclosed by the Gaussian surface inside the spherical shell. Therefore, this will be equal to 0. Okay, which means this term goes to 0. Then what we are left with, that is the integral minus of the integral infinity to R, 1 by 4 pi epsilon 0 q by R square dr. The same we have evaluated in the above case, that is, see here, we have done the same integration here. What we obtained the answer? We obtained this answer, that is 1 by 4 pi epsilon 0 q by R. 1 by 4 pi epsilon 0 q by R. This is a V inside. Okay. this is a final expression for the electric field inside a uniformly charged spherical shell. If you compare the V inside and the V surface, this both are same. Both are the Q by R. That means electric potential at the surface of the spherical shell is equal to electric potential inside the spherical shell. Electric potential is constant inside the spherical shell. If I want to write this expression in terms of the surface charge density sigma, then I have sigma is equal to total charge divided by total charge contained on the spherical shell, that is 4 pi square. Then this Q is equal to, I will get the same result that what you have obtained earlier. Sigma 4 pi R square is V inside, I can be written as 1 by 4 pi epsilon 0 sigma 4 pi R square divided by capital R. This 4 pi cancel, this R cancel. Then on the surface you will get sigma R by epsilon 0, exactly same as that we have derived earlier. Okay, this is the way of finding out the electric potential of various objects.